Okay, thanks for coming. I'm a computer scientist by training. I've been a data scientist since the time when data science started making more money than software engineering, so about 2008. And my main claim to fame is a R package for Hadoop, which had a ridiculous number of downloads, but probably only 200 users. But that, unfortunately, that was not in Python. So I do APIs all the time. That probably was the moment where I did the API for the largest number of people, and I finally decided to write a package to help me write APIs. So that's what I'm going to talk to about today. So APIs are a very complex subject. You know, you find books about them. Somebody was talking about them before, in the previous session, and I see there's Raymond Hettinger has a 1 hour, 2 hour video about APIs, a lesson learned online. This is much simpler. I'm just talking about a single package that's actually fairly simple. I think I'll cover all of it, all the possibilities today, or 90% of them. How is that possible? And the trick is I focused on a small subset, on a small sub-theme of good API design, which is consistency. And by tackling that, I think it's small, but it's important enough that it was worth writing a small package for it that helps you be consistent in your API. And I hope from that good things come as far as being orderly and putting together a good API. So by consistency, I mean both syntactic and semantic. Syntactic is order and naming of arguments, essentially. And semantic is the stuff that happens early on in the function. So argument check-in and possibly conversion, I think. And also there's a little bit about metadata. Essentially, the documentation itself is covered in this package. So the idea is, if you think about, consistency is good because it's easier to learn that messiness. If a function, if a library has a bunch of functions and they all put the same arguments but in scramble order, it just drives you nuts. So by being consistent, you lower the learning curve, you reduce the possibility of errors. And if you think about the libraries that you love that are well known, I don't know, like pandas or dplyr for R with the famous verbs. There's a family loop that's the first argument is typically a data frame because those are data libraries, and it's called typically data because it can be any kind of data. It's not like a specific data frame with 5 columns, it's anything. And so the name plainly suggests what's supposed to be there. So consistency is good. It's probably not good in absolute. It's a trade-off with other properties of the library, but it's good to have. So what happens in Python is that you can't express consistency. You achieve it without expressing it. There's 5 definitions. They look similar, and if you're intelligent, and you all are, and if you're observant, I should say more than intelligent, you see that the 5 definitions are very similar or identical, and you try to keep them that way. But it's not written anywhere in the program that was the case. And then your coworker, the guy who pushes the beer cart at 5 p.m. on Friday, comes and does a check-in at midnight on Friday and changes the 5th function, and now they are no longer consistent. So with Autosig, the package won't load anymore, so you solve that problem, right? So by putting these concepts of consistency in code, in Python object, by simply applying good programming, typically don't repeat yourself, you achieve consistency. And you achieve it in a durable, maintainable way. Enough talk. Let's not look at the dunes. Let's look at code. So this is the online and documentation for the package. Or read the docs. It's a toy library. Let's focus on the definitions for now. It's got map, reduce, and filter. And the first 2 functions have 2 arguments, a function and iterable, that are exactly what the name suggests. And then the third, that's the beer guy, checked in the filter, and it's iterable fun. So there's a change in order and a change in naming convention. So we can discuss until the cows come home if it's better to have the function first or the iterable. There are some weak arguments for one over the other, but we can also discuss about long names versus short names. functions versus fun. It's more readable, more writable. Is it necessary to have a long name? In that case, it's kind of obvious. Very philosophical subjects. Sorry, open to opinion. Mixing and matching these different orders of arguments and these different naming conventions inside the same library, most likely a bad idea. So if you want to violate consistency, have a good reason. It happens, there are good reasons to do it, and the library allows you to do it, but it's better if you think about it. If you don't think, just stay consistent and things will be all right. So let's look at the bodies instead. This function starts with two asserts. So it's checking the type of its arguments. And we couldn't call that style paranoid, without being disrespectful to anybody. Essentially, I'm not trusting the preconditions are satisfied before the call. I'm not trusting the caller. I want to check them myself. Here you have the reduce goes straight into the meat of it. So it's a more optimistic function that delegates the preconditions to the caller. And here we have a filter, and these 4 lines are all CRUD, essentially. The filter is here, but these 4 lines do attempt some conversions. Exactly what it does, it's not important, but essentially it's an accepting function, tries to make a function iterable out of thin air if it has to, and it will fail only if it really has to. Maybe you've heard it as a Postel principle that applies more to network protocols rather than functions, but try to be to break only if absolutely necessary. So which style is best? I don't know. I think there are contexts in which each of which is good, but I know that mixing and matching them in the same library is very confusing and produces errors. And the other thing I know is that I don't like to have to write these things every function just to keep them consistent. Even if I reduce the checks to one function, I still have to remember to call it. And maybe once per argument, or maybe one function that does the checking on all the arguments. It's just not something I want to deal with at the beginning of the function. I love to go straight to the pure logic of the function. All right. So you can fix this by good discipline and with your editor, your fingers, and the technology that Raymond mentioned this morning. It's called cut and paste. But let's see how it's done with Autosig. I think there is a better way, and I tried to provide it. So let's focus on these imports for now. I'm importing param and signature. Here I'm violating my own rules because one is abbreviated and the other is fully spelled out. And I had a very good reason to do that. But let's gloss over that. So this creates signature objects. This creates param objects. We'll see what they do. But the main concept is that these things that you read in Python books now are live objects in Python. You can copy them, you can give them names, the most important thing. You can create collections of them if you need to. I don't have an example of that, but and so you can compute with them. And here I'm taking those 2 conversions and putting them in functions. Nothing specific here to Autosig, it's just good coding. If I intend to make the conversions in every function, in map, filter, and reduce, I should have a name for them so that I can reuse the code. And here is the crucial point of Autosig, creating signatures. So we have a signature that has 2 arguments that, guess what, have the same name and order as the arguments in the definition that we like, the one we want to keep, and not the one we want to correct. And then they're initialized not just with the default value, but a more complex object, parameter object, that contains or carries a converter and a validator. I stick them right there in the parameter object, then I stick the parameter object inside the signature. Now I have all that stuff nicely packaged, both the syntax and the semantics, which would be the converters and checkers, packaged in a signature. I give it a name. The most important thing is giving name to things so that we can use them more easily. And here we are down to the action. I use the decorator Autosig because I was running out of names, so I named the decorator like the package. And I give it as an argument the signature, and here follows a definition. Wait a second, I say, now I have to repeat the definition. Yes, there's no way around it, at least I couldn't find one. But that definition has to be like that. So it's dry, not in the sense that you don't need to write it, but it's dry don't repeat yourself, meaning that that's exactly the only thing you can write there. There's no room for error. And semantically, just using the decorator means the validator checkers are automatically activated and will be called first in as the function get executed after the arguments are evaluated, but before the first line of the body. Okay, again here with the, so you see the map function now has lost the CRUD, the asserts here at the beginning. We go straight to the meat, which is what I like. The reduce function was already down to bare bones to the meat because it was an optimistic function, optimistic, sorry. But in the behind the scenes, the decorator is guaranteeing not only that the signature is correct, but also that the validator checker are invoked at the right time. And finally, the filter, I have to fix it because now it has to comply with the signature. And so the beer guy would break the test if he tried to change that signature. Actually, if you violate the signature, your code will fail at load time, so very early on. The syntactic part. Okay, so this is a toy example, and let's see a real example, which is the only user so far of this library, which is my other library, Altair Recipes. Altair is a beautiful graphical library for Python. It's based on Vega. It does grammar of graphics, interaction, and online visualization. Those were the three conditions for me to pick up a new graphics library, statistical graphics library for Python. So I focused on this one. Why not write a package on top of it to learn it? So Altair Recipes, which is my package, not Altair, is a collection of classical statistical graphics defined on top of Altair. So you see there's an autocorrelation. This is documentation. Box plot, which it seems simple, but it's 20, 30 lines of Altair. Another box plot here with colors because it's pretty. Bar charts, heat maps, other heat maps, histograms, layered histograms, and so on and so forth, right? So this is a statistical graphics library. It's got an API. How does it look? You see, there's a very trivial. There's a very trivial sounds negative. Very simple. There's one entry per statistical graphics type with a bunch of parameters. The first is the data. Then there's some selectors in that. Data is supposed to be data frame. So there's some column selectors here, some statistical parameter which is specific to autocorrelation, and then a height and width, because eventually you have to end up with a rectangle, right? So autoplot is kind of magic that will select the statistical graphics for you. So let's ignore it for now. It's one of the cool things of Altair Recipes, but it will be a long story. Then we have the bar chart. It's got data here as a first argument, but then there's X and Y because a bar chart can deal with two random variables and display two random variables. It's got color optionally here and the height and width. And let's look at another example, box plot. Now the selector is slightly different, columns, because box plot can represent multiple random variables, any number, but I mean largish. Group I is when you have wide or tall data. And then again, use of color, height, and width. You see commonality and differences. How do we stay consistent without being hamstrung, in one single definition? That's where Autosig comes in. This is the code. You see there's about a file for each main statistical graphics type. And then there's exception, the common is a little bit common library. But the interesting one is the signatures.py. So now I have a single file that describes the API, the things that the user comes in contact with, and I can centralize it there, and make the central, authority for the definitions about the API. It's not scattered all over the place, so it's harder to make mistakes. It's all there. Let's look at it inside. So I define a main signature that I call recipe because the package is a bunch of statistical graphics recipes. And it has an argument data, an argument height, and an argument width. These were the first argument and the last two, but were the ones that were common to all the different statistical graphics. You start with some data, you end up with a rectangle full of colors. That's what it is, right? And so this is the basic signature from which everything else is built. It's got a data argument. Okay, I just said that. Each of them is initialized with a parameter object. Parameter object carries a bunch of things that some of which we've seen, like the converter, and some of which we haven't seen yet, like position. So position of arguments in the signature is by default the order in which they are passed to the signature constructor, but I needed more flexibility, so you can also specify an integer position. And here you see the position of height is -2, which means I want it to be one before the last. So different length signature, I can place the arguments from the beginning or starting from the end. And width is expected to be the last one. And then another new feature is default here, which is exactly like Python default, but it can be specified here, or actually has to be specified here. And the docstring. Why not attach a docstring to an argument so that we don't have to repeat the docstring every time we pass that same argument to a function that will take a data frame anyway. And so we have drive for docstrings, which I think encourage me to write better docstrings because I don't have to fix it up 52 times. All right, so that's a fundamental, basic signature. How do we go from that to more complex ones? So here I define by partial application. So it's a way to constrain the behavior of a function. I don't know if you're familiar with this. This is just functools in Python. It's nothing I invented. So I wanted a version of the param constructor where the validator is always to column. And that's what partial does. So column is also a function that returns a parameter object, but the validator argument is gone. It's fixed. So I wanted to be able to say whenever I create a new column, I want the validator to be stuck there to that value. And then we have three derived signatures here. Univariate for when you have only one statistical variable involved, bivariate for the case of two, and multivariate, which is for the case of one or more. Now, this is a little bit of a mouthful, but statisticians use these words for breakfast, so that's why I use them. But it's just three signatures that extend the basic signature with a bunch of arguments. So this one has, the univariate has just one column. The column has got its own default position and docstring. The bivariate recipe has got two additional arguments, x and y. They come in position right after the first argument, the data, and this one is the next. And the default is the first column of the data frame and the second column of the data frame. Makes sense? Put a nice generic reusable docstring here, and off you go to the last case, multiple columns. So we have another parameter object here because the columns can be initialized with a list of integers or strings. So it's got its own converter, its own validator, and then so on, so forth for group by. Okay. Now I'm going to prepare a bunch of, by partial application, I want to prepare a bunch of other parameter generators here for when I have to use color, and I stick the docstring here. Use color is a Boolean argument that I'm going to use over and over again. It's got default, converter, and docstring, and opacity and tooltip. So what you notice here, I'm not setting the position because that's kind of the one that you set at the last minute when you're putting this signature together. So that's what's deferred to each file. So with this in hand, we have a main recipe, a main signature, three derived signatures for the three main cases of one, two, and a general number of random variables to visualize, and a bunch of special parameter constructors for special cases. So how do we use this? This is the file, the autocorrelation, the source for the autocorrelation statistical graphics. And here I generate a specific signature for this function, so that it doesn't have a name. I'm not assigning it. I'm just using it because I never use it again. And the only difference is that it adds this max lag parameter, which is specific to the concept of autocorrelation, and it's not used anywhere else in the library. And it's got its own default position docstring, and here with the decorator, I apply this signature to this function. The resulting signature, which I have to spell out here, is data followed by column, max lag, height, and width. Then you observe the super microscopic docstring here, because I don't have to redocument all the arguments. That's a given. And here, believe me, I don't think you can read the code here on the fly. This is the actual core of producing an autocorrelation graph. It goes straight into the meat of the function. Another example, and then we're near the finish line for this is heat map, I think I picked. Yes. Let's go down to the signature here. We start with the divided recipe because heat map starts with 2 random variables, and we extend it with 3 more arguments, the color, and here we only have to specify default and position. Everything else has been already specified in the signature file, opacity, and aggregate, which has to do with the statistics of it, nothing directly with the graphics. And the resulting signature is here, data followed by X and Y because it's divided, then color, opacity, aggregate, height, and width. And again, no validation, no checking at the beginning of the function, just a very short docstring, and then we go straight to the meat of the function. Here it is. So pretty much you know everything there is to know about this. This is for everybody who's writing APIs that are more than trivial, I think, and they're worried, concerned about consistency. And 2 things where I think where I could actually 3 things I could add to this library are return values. They're part of the signature and they're pretty much ignored here. So that has to be part of it. Another thing, maybe something related with a life cycle of the signature. I haven't thought about it, but if you want to change things, can you help maybe with the deprecation feature or something like that, so that you can deprecate an argument? And another thing is that this right now can only be applied to functions. There's no reason other than laziness on my part that it doesn't work on methods yet. So I think the same reason, for the same reason, it should work on also on methods. Now, if you have an object with a huge number of methods that require a treatment like this, maybe you should switch to smaller objects according to some theories of object orientation. But I think in principle, you should be able to have some consistency also in the signatures of methods of objects. So, and it's an experiment. I don't know of anything else that's comparable, even in other languages I've worked in. So it may be a very great idea, or it may be forgotten after this talk. I'm not absolutely sure. But I like the idea of making it possible to name things. As Raymond was saying this morning, you see a pattern, you move it to another part of the code with cut and paste, right? And you give it a name, and then you spread the joy across your code base. And that's one of the core activities of programming. And now you can do it also with API elements. You see a good pattern, you give it a name, and then you apply it around your code, and you make it more beautiful. Thank you very much.
For the remaining time, we'll take questions. If anyone has a question, please raise your hand.
Yeah, you mentioned about the doc strings. Since you're defining them in this signature here, sometimes when I'm using VS Code, I'll just highlight a function and it'll just kind of show me the signature, the doc string for that function. I kind of see what all of the arguments do. Do I get the same functionality?
Yeah. The decorator will assemble a traditional doc string. And you can see here in the read the docs, for instance, there's completely traditional doc string at the end of once you loaded the package, it's all normal objects. You see the same string is here, and every time every IDE, I mean, I haven't tried all of them, but both PyCharm and Atom have no problems. Of course, the pattern interpreter, it's just a doctrine. It's just assembled at load time from pieces. That's it.
Right, do we have other questions?
So I have a question. So I kind of, so in my code, most of those assert statements are in unit test. I mean, I understand how this is different, but like, how do you see the unit tests fit into the Autosig kind of pattern?
Yeah, it's the question is normally asserts go into unit test. Why do you put them in a function, and how does that relate with Autosig? So that's a paranoid style, and the idea is that you don't trust the outside world. So if that argument comes from a library that you don't trust, or comes from the outside world, you want to have a gatekeeper that check that will fail immediately if the argument is not correct. In the unit test, it's different because you're trying to catch an error, right? If you put the same assert in your code, it's an attempt to fail fast before you do produce any disaster. So it's when you do, for instance, scientific code, the worst thing that you can do is to publish bad data, and you start believing things like starving makes you live twice as long, or all sorts of things can happen, right? And so, but if it fails, well, the worst case scenario is that your advisor gets angry with you. It's not a big deal. You won't do something like that in a crucial online service. When the argument comes in wrong, you place an assert in there, unless you're writing in Erlang, you have your robustness outside the process, and you're happy for things to fail fast while in trouble without creating any complication. And some other outside mechanism will restart the process. Because the worst thing that can happen in distributed system is parts that fail gradually in incomprehensible ways. So best thing is everything works. The second best thing, if something doesn't work, it degrades gracefully and sends signals for help. And the next thing is that it stops working right there, and then you have a leader election or not. And the next worst is unpredictable types of failure, and the worst is adversarial, somebody who's trying to mess up your system. So sometimes failing fast, just as soon as a precondition is not satisfied, is the best thing. And typically in research code, you're happy with that. Just the analysis, there was a mistake, I don't want to see the results, I just want to fix it. Sure.
Anyone else have a question?
Thank you. Thank you very much.
Thank you.